Okay, let's get some practice identifying the arrow pushing pattern, and this is going to be similar to the Skill Builder 6.3. So here I've drawn 5 different reactions, and if you want to pause this and take a few minutes to try to identify the patterns, we can then work through them once you press play again. So for the first pattern, we want to observe that there was a bromine attached, and now there's a bromine as an ion that's separate from the carbon structure. And so that looks like loss of leaving group. So the loss of leaving group pattern will always show one thing breaking into at least 2 pieces. And so we can show that arrow pattern with a single arrow, which starts at the C-Br bond and pushes those electrons onto the bromine, forming the 4th set of lone pairs on bromine. So of course bromine starts with 3. My red arrow shows a 4th lone pair forming, and of course this carbon here lost a bond, so it's now a cation. So this is loss of leaving group. The second pattern takes this alcohol and turns it into what looks like an alcohol with an extra hydrogen on it. So this is probably the proton transfer arrow push, and of course that's going to involve 2 arrows. We're going to take the lone pair on the oxygen, use it to create another OH bond, and then we're going to take the original OH bond and break it, push it back onto this O that's part of the H2SO4 molecule. And you'll notice that I drew H2SO4 with a couple extra bonds here so that I could show these arrows, but really my acid here is just a different way of drawing H2SO4. And then that results in a 3rd bond to oxygen, so that's a cation right there. And I have my new hydrogen as one of these, it doesn't really matter which one. And then I'm left with HSO4 minus. So this is a proton transfer mechanism. Now it looks like the acid might be participating in a loss of leaving group pattern where the HSO4 minus, this portion, is leaving due to this arrow. And that is true. However, this pattern is more specifically called a proton transfer mechanism or pattern because we're actually moving this hydrogen from one molecule to another. So this is most definitely a proton transfer. It does incorporate elements of loss of leaving group, but it's most correctly called proton transfer. For the third one, we can see that there are 2 molecules here and we've turned them into 1 molecule. So that's probably going to be nucleophilic attack, where the nucleophile attacks an electrophile. And of course, we see that this bond is new. The OH then, of course, attacked this carbon. And that carbon couldn't just accommodate an additional set of electrons. It needs to lose something, so it's going to lose the pi bond, push it towards the carbonyl compound. And then the carbonyl also has to lose something, so its pi bond goes up onto the O and creates the O minus. And so now we have this compound here. And if you're having trouble following this, sometimes it's helpful to number the carbons, and then we can maybe more easily keep track of them. So here you see that carbon 4 formed the bond to the OH, and that's what we saw. Also, we might have trouble starting this reaction out. It looks quite complicated, but I hope you'll notice that this red arrow here could be a resonance arrow. So let's look at the resonance patterns of this compound. So one of those patterns is pi bond between 2 dissimilar elements. We have that in the CO bond, and so we might make this this ion, this compound. And another pattern is allylic cation, so we could form another resonance structure, and that would give us this. And those are the 3 main resonance structures that we'd expect here. But can you see how this compound might be really reactive towards nucleophiles at that cation on the right side? Right, this cation is essentially the cation that's formed right here on carbon number 4 in our original picture. And so the OH minus is attacking that carbon. We could also draw the OH minus attacking the carbon in the resonance structure. So if you get stumped, we'll say, you can always try drawing some resonance structures of your carbon structure and see if that might help you decide how things proceed. And of course, these 2 arrows right here, and right here are found in this arrow and this arrow. So we see all of our arrows here. We've just done them in several steps in terms of resonance structure. So it's a good strategy to sometimes think about, this molecule looks strange. Let's think about its resonance patterns and its resonance structures, and that might open up a possibility or help me decide how this OH would react with it. In this case, we see that there's a partial positive at carbon 4, and that can lead us to deciding how the reaction proceeds. So the fourth reaction, it looks like this cation is moving. And of course, you might be tempted just to draw this arrow. Please don't do that. That is incorrect. There is no lone pair at the cation, so we cannot just move the cation. However, we could recognize that there's a secondary cation here, a tertiary cation in the product. And if I take this hydrogen with its CH bond, so if I move the hydride, the H minus, I could do a hydride shift that is classified as a rearrangement, and that's going to leave behind the tertiary cation right there. So we're going from a secondary cation to a tertiary cation. So this is a rearrangement. The last structure also involves a secondary cation going to a tertiary cation. It looks a lot more convoluted, though, than the first rearrangement. But I think you'll agree that if somehow we could lose one of these bonds at this dotted carbon, that would become a tertiary cation. So that's going to be where this tertiary cation ends up. And it might be useful to maybe just number things and see if that helps us follow this reaction. So the two methyls are going to be 1 and 8. And then this is probably 7, 6. So numbering carbons can be a useful strategy to solve many different problems, as you've seen a couple times in this video. So now it appears that this bond between 2 and 6 needs to go away. And so what we need to do is do a alkyl shift. I'm going to take that bond and push those electrons onto the cation at number 7. And that's going to leave behind an empty p orbital at carbon 2. It's going to create a bond between 6 and 7, which is what I see right here. And so this is also a rearrangement, but this is an alkyl shift. And these are often the hardest either to recognize, as we saw here, or to predict what their product will be. So I encourage you to use this numbering scheme to help you. So you look for certain landmarks on the molecule, and our two methyl groups are good landmarks here. They are not going to be affected. Maybe their location will be affected, but not the fact that they are methyl groups. That is not affected by the reaction. So maybe do some numbering, and you don't have to number according to IUPAC rules. You just have to number so that you can match up the same numbers in the product. So really the numbering scheme is up to you. Just use it as a tool to help keep track of how the reaction proceeds.